So even before you started in this class, I'm almost certain most of you guys had heard or had seen or know what sine looks like. So most of us know what a sine wave looks like, right? So it wasn't surprising when we actually plugged numbers in. It wasn't surprising to sure enough to see it doing that, and it just does that forever. Because does anyone remember when we graphed sine? I know this is last Thursday. What we decided to start at and go to, because the thing about sine and cosine is, in fact, all of them, is they'll have a shape, and then they'll just repeat that shape forever. So in order to graph it, I don't graph it forever, dear God. Just use infinite tape to tape pieces of paper together so we can do the whole. No, we graph one cycle, and then just say it goes forever. Leave me alone. Yes, we just put little arrows at the end. Does anyone remember where we decided to graph our base shape starting from 2? And if not, we'll talk about where we want to do it. I love you guys. Can somebody tell me in a circle, where does it kind of start, and then how much do I rotate to get to the end? In radians. Where does it start? A circle. Before I moved at all, how many degrees or how many radians have I gone through? 0. And if I go around the whole circle, how many radians have I gone through? So it kind of makes sense. If I'm graphing something, very often, if we have a choice, we pick to graph close to 0. And I really want you guys to understand this. Since it repeats the same shape, that shape right there, for sine, it's going to repeat this shape forever. I just have to graph one piece of it and then put arrows. And I'm not going to graph the piece that's way over here at 78 pi. Why the shit would I do that to myself? I'm going to graph the piece that's way over here at freaking 0. Yes? So I can kind of look at me go. My y-axis, my x-axis kind of look, and then graph, right? I could graph the one over there. Why would I? So are you guys kind of with me? So for both sine and cosine, the way that I teach this is I go from 0 to 2 pi. So just to remind you, we did this last Thursday. We made a table of values, and we found out that, of course, sine of 0 is 0. What's sine of pi over 2? No? Where's pi over 2? Where is it? Can you do it in the air? Where is it? Like, here's 45 degrees, right? That's pi over 4. Where's pi over 2? Like this, yes? So what's sine of pi over 2? 1, because it's on the y-axis. It loves it there, yes? So the output for an input of pi over 2 is 1. What's sine of pi?
0.
Why?
Because it's on the x-axis.
Yeah, pi is on the x-axis. It's an angular measure that kind of references the x-axis. Sine hates it here. It loves y. No y here. 0. Turtle, fully in shell. Yes? Are you guys with me? Aren't there a lot of points between those? And didn't we, if you remember last Thursday, we got kind of detailed. We did pi over 6, pi over 4, pi over 3. We did all the damn things. We got these funky 0.7, 0.9. You guys with me? So of course there's infinite points between those two, but why am I picking these? What's special about the ones I'm picking? You could do it. Why are they nice for graphing? If I'm going to graph something that's doing this, what is one of the most important things to know? Where it's going to turn. Yes? So obviously I want to do this, and I also want to do this. What's sine of 3 pi over 2? -1. So I want to do my extremes. I want to do where it's turning. And in general, I also want to do x-intercepts. X-intercepts, we almost always want to find that, yes? In fact, if you go back to when we were graphing polynomials, one of the first things we did was, what's the x-intercepts? So there's an x-intercept, there's an x-intercept. Because those three are all x-axis kind of referenced angles. These two are y-axis. That's why they're extreme, big, and small. Okay. So how do I introduce this? So then I just fill it in. We do go through 0.7, we go through 0.9, we go through all that. That's still in there. And that scale kind of sucks, but it's okay. And then we just put little arrows at the end that just says, you see what I made? Keep going. And that's what the little arrows mean. So let me ask you this. If I start at 0, I'm going to ask kind of a strange question, but let's see if you guys catch on. Because this is a huge part of doing this. How many steps did I take to get to the end? How many plotting point steps did I take? If I start at 0, how many steps did I take? Yeah, 1, 2, 3, 4 steps, yes? Let me stop for a minute. You guys with me? All right, listen, that seems kind of silly what I just said. You're not going to believe this, but it's going to be huge. It's going to make graphing these much easier than it could be. So what did I just graph? What is that the graph of?
Sin.
That's the graph of sin. No, isn't it? Do you wonder what sin looks like? So this is the graph of sine. So have we ever discussed like smooshing a graph? Have we ever talked about that? Or stretching a graph? Okay, so we could do that here. And in fact, the funny thing with sine and cosine is to me they make more physical sense. They look like springs. So I can consider squeezing a spring, stretching a spring. Yes, the coils get bunched up and then the coils get far apart. So I mean, if I cut this in half, if I smushed it by a factor of 2, are you guys with me? Does anyone know what the function would look like if I wanted to smush it by a factor of 2? No. Believe it or not. If I put a 1/2 like in front of the sine, okay, I really want you guys to think. Let's do this. Let's remember if I did this, what would that do to the picture?
Shift it.
Which way? No. Right one, yes? You guys remember that?
Yeah.
And if you forget, it's weird because you're like, Jeff, I don't know if you noticed, there's like a minus there. Mr. Waller, if that's your real name. But of course, what was the idea? What did I have to do for my poor little inputs to make them be able to handle somebody taking one away from them? I had to make them one bigger. That's why the whole thing goes right. So if it's inside with the x, the result is the opposite of what it looks like. So if I wanted to smush it, what would I have to do? Nope. That. Is that inside with the x? Yes. It's not shifting it left or right because it's not adding or subtracting. It's multiplying, and it's the opposite of what it looks like. If I double all of my inputs, they could all be half as big. If you needed $20 for something, and I'm like, I'll double whatever you got, how much do you actually have to give? 10, half as much as you used to. So this would, is everybody semi with me? Let me say this. I am about to remind you what all the transformations did. We're going to end up creating a process where we don't have to apply the transformations one at a time. It's going to be a little bit of work, but the end result is when I actually start graphing, that's the easy part. But I just want to remind you what all these things do. So, can somebody tell me? I'm going to cut everything in half, left and right. So, where would this go to? Pi. Is that cool? Goes half as far. Where would this go to? This is where things get a little bit wonky. I'm sorry, this here. Where would this go to?
In between pi.
Yeah, what's half of 3 pi over 2? 3 pi over 4. So that would go here. It just gets smushed by a half, yes? It's like the accordion, and I'm smushing. I don't think they call it a smush when they actually play it, but that's okay. Where would this go?
1/2
Pi over 2. Where would this go?
pi.
Pi over 4. Good. And of course, this would go nowhere, because half of 0 is 0. So now it's going to look like this. They make that big. There we go. And then we keep going. How many steps do I still take, though?
4.
1, to get to the max, 2, back to 0, 3, min, 4 steps to get back to 0. So do you guys see, no matter how smooshed it is or how stretched it is, I'm still going to take 4 points, 4 steps. And what's really cool is, where does sine start? 0. First step takes me to the maximum. Second step takes me to 0. No matter how much I've stretched it or compressed it. Ooh. Okay. What would happen if I don't think these different colors necessarily show up for you. What would happen if I did this instead? Yes, when it's outside, it's up and down. When it's inside, it's left and right. So if there's a multiplier inside, that compresses it or stretches it. When there's a multiplier on the outside, same thing, just up and down. So this would obviously do what? Yeah, make it go higher and lower. Yes? Before I get there, our original sine function, does everybody see what somebody might call a midline? A midline. Do you see how the sine function is oscillating around a middle? And I just heard it. What is the midline? X-axis. Is everybody with me? Okay. So before I get too far, we say that this, what would you say the amplitude of this is at the moment? 1, good, because the amplitude is measured how far away from the middle does it get. So what's the amplitude for this guy? Holy shit, because it just stretches it by a factor of 2. So the only effect that this would have is the original here would just go up twice as much and down twice as much. So now it would look like, whoa! My scale sucks here. Did I go the wrong place? I lost track of my original. Okay, that's okay. I have too much happening on one picture. So if I do it again real quick. Hi, 2 pi over 2, 3 pi over 2. Let me make this a little smaller so it's a little bit easier to control. Okay, there's my sine again. Just want to redo that one. Okay. Now if I apply this to it, it's just going to double all the outputs. And of course all the zeros are the same as they were before, so now it just goes up and down higher. Yay, Jeff! Okay. Is everybody with me? Thank God. But you can imagine, trig functions are a little bit trickier, and if I apply every possible transformation at once, I really don't want to have to apply each one of them. So let's develop a better method. So remind me, for sine, what input did we decide to start at? 0. And what input did we decide to end at? 2 pi. So any sine function you ever see in the universe, it will begin when the inside is 0, and it will end when the inside is 2 pi. Is everybody with me? In fact, I could kind of do this up here. I wish I hadn't drawn this. I'll be all right. Can everybody still see my sine 2x here? Yes? When the inside is 0, this will start. That's why we started at 0. Because when x is 0, the inside is 0. When the inside is 2 pi, that's when it will end. How do I solve this for x? So when is it supposed to end? When the input is pi. When did our shape end? Pi. So I could actually, if I'm given something with a lot of weird shit happening on the inside, I could just set it equal to 0, set it equal to 2 pi, see where it starts, see where it ends. That's really good information to have. Instead of graph the original, pick it up, smoosh it, move it over here. Oh my God, I don't want to do every single thing one at a time. I want to have a way to kind of like get to the end. Yes? And all of you are like, that's what I do every day, man. Just want to get to the end. I understand. So let's do this. Let me introduce a couple other things. So we have a way to figure out where it begins and where it ends. We have a way to figure that out, given any sine function ever. What is the period again? So let me put little arrows so we're looking at the right one here. That's the original sine, yes? What's the period mean? What's the definition of period in terms of these trig functions? It's, who remembers? Anybody? Or have I said this yet? Oh, there you go. You can say that. Remember, I'm teaching them that we're basically doing all the same stuff right now in the other class. I know already, Period just means how long does it take you to make one representative shape? So how long did it take us to graph one representative shape? 2 pi. And then the whole thing would just repeat again, yes? And that would take 2 pi. So every little chunk of repeated shape takes 2 pi to graph, yes? What about when I did this? Did it still take 2 pi? No, it took pi. It took half of what it did before, yes? Okay, so here's one thing we can focus on. What do you guys think about if I had this? How would you figure out the new period? What do you think? No. I don't want to know beginning and ending. I just want to know the new period. What was the original period? What's the period for sine and cosine? Those are basically the same thing. 2 pi. That's what we said. You guys with me? Write that down somewhere. That's you. Sine, cosine, both have a period of 2 pi. And then if I smoosh it or stretch it, then it's going to change. What did we say this does? Divides. Okay, what you just said is what you do. What was the period to begin with? 2 pi. And of course, what do? When I multiply by 4, I divide, just like we cut in half just a minute ago. Yes? So what would the new period be for this guy? Pi over 2. So it would do this, but it would stop here. It would fit everything in here. So I just keep smushing it. Yes? I just keep compressing it. Yes. Okay, maybe. So let me just lay this down right now. What you're going to see is I could put whatever number I want to there, yes? Let me put one more number there. What if I had this? How long would it take it now to do a complete... this is actually called a cycle. It's also kind of related to the wavelength, but what would we do here? What do you guys think? What did we do when there was a 4? We divided by 4. So what are we doing? There's 1. We divide by half. But how do you divide by half? So if I put a 4, it's going to cut in fourths, because when it's inside with the x, it's left and right, and it does the opposite of what it looks like. Because if I have a 4 times here, these could all be 4 times smaller. So that's why it compresses it. So it makes sense if I put a 1/2. Now all my movements have to be twice as big. It's going to take it twice as long to get all the way through. You guys are all. So in general, we kind of make a rule out of this. If I have a sine function with a multiplier, and we'll call it k, because that's what was picked for us. How do I get the new period always? I just take the old period divided by k. That's silly. That one step, and I know how long it should take to make that shape fit. Now here's the next thing, and the next thing is basically going to finish this out. What did I say a minute ago? Let's see. How many steps do I always take to get the highlights? 4 steps, right? Start at 0, 1 step max, second step 0, Third step min, fourth step 0. Okay. So let's see. Let's analyze this. So if I had sine of, doesn't matter, let me think. That doesn't matter. We could do anything we've already. So 1/2 x. What did we figure out the new period was? 4 pi. Now, can somebody explain to me again what that means? Yeah, I'm with you. But, and then what about this? So instead of 2 pi, it's going to take 4 pi to do what? Yeah, to make a complete picture, yes. You guys are going to go up, come back down. It's going to take, and then of course, when you get to the end, it does it again. And it takes 4 pi for that one, forever. Until everybody goes crazy. How many steps do I take to hit all the highlights? 4. How big is each step then? If I have to go 4 pi, then I take 4 steps. How big is each step? So what do I always do to figure out what I call step size? I take the new period. That's how far I've got to go. I need this to make physical sense. That's how far I got to go. Divided by how many steps I want to take tells me how big each step is. How you guys doing? Again, just if it's not really coming together yet, I don't blame you. There's kind of a lot of parts and pieces. I'm going to do a whole problem here in a minute, and then you're not going to believe this. I have a handout. So let's see this. Can somebody tell me how to figure out where this one begins? Yeah, how do you know it? It begins when the inside is 0, and of course to make that 0, you make x 0. How do I figure out where it ends? The inside has to be 2 pi, and how I solve that? Multiply by 2, I get 4 pi. Now why does this make sense? Because we already know that the period is 4 pi, so it should take 4 pi, yes? So I begin at 0. How big is each step I take? Pi. And I take a step of pi, I take another step of pi, I take another step of pi, I take another step of pi. Did I end where I was supposed to? Yes, for 2 reasons. 1, 2, yes? So, eventually, we're going to realize that this work here is extra. I don't need this work. But when you're first doing this work is cool to do because it verifies everything else. Are you beginning where you're supposed to? Because one thing we haven't done yet directly is shifting it left and right. And that's where things get a little bit funkier. So what this is sine. So what does sine do at its beginning? Where's sine at its beginning? Is it up here? Is it down there? At the beginning, what is sine doing? It's at 0. Do you guys see that? So that is something you have to memorize. Sine starts at 0. We're going to see what cosine does here in a minute. Where does it go next? 1 step in, where is it supposed to be? At the max, yeah. In this case, I didn't change the amplitude, so that'll be 1. 1 more step, where does it go? 0. 1 more step, where does it go? Minimum. 1 more, no. Okay. And that gives you that shape, yes? That part's not hard to memorize. It's just when you plot the steps, you just have to put the major things, the max, the min, and the zeros. And then you just fill it in. You just make the point bigger. Fill it in. Wow. Whee. So the actual graphing is easy because all of the work is here. And each step we just did by itself wasn't that bad. And on a test, if I say graph sine, I'm not just going to say graph this. I'm going to say graph this after finding the amplitude, the step size, the new period, blah, blah, blah. So I remind you all the things you should find. Okay. So let's do this. Next step up. what would this do to the normal sine function?
Shift to the right.
Right pi over 6. And that's just a horizontal shift, yes? But here's what we call it with trig functions. We call it the phase shift. Have you ever heard of something being out of phase? Very often you hear it in like sci-fi movies. He's out of phase, we're gonna do it now. He's on in and out of reality. So out of phase simply means you have one thing and you have another thing that's not starting in the same place. So when I shift it by pi over 6, it's now starting in a different place. It's out of phase with the normal sign. Yes? In fact, here's what's really cool. Do you guys have headphones at all somewhere in your life? Or do most of you guys have earbuds? Do you have headphones, like actual headphones? Do you have like ones that are noise canceling anyway? If you don't, have you heard of noise canceling headphones? Are you curious how they work? Because they do cancel noise. So what's really cool is the headphones take in the sound and then they generate. So here, it would take in sound, and the sound might look like this. Because sounds have frequencies and so forth, and the frequency is basically, this frequency is higher because it goes through its waves quicker. That's a lower frequency. This would be this would be okay. And what the noise canceling phones would do is it would make it would make another waveform that looks like this. So these cancel out. They cancel each other out. Isn't that kind of cool? This is what's called destructive interference. So when you add these two together, you get this flat line. And normally, if there's like an abrupt change in sound, you might hear a little something because it takes a second for it to generate a new canceling wave. Is anybody, are you guys with me? I'm not gonna suddenly say your next assignment is construct noise canceling headphones. No. But you kind of get what I'm saying here. So that would be, it generates a wave function that is completely out of phase with the incoming wave functions. Now, it's a little more complicated than this because there's more than one noise coming in. But effectively, that's what it's doing.
Would that be like, if the original is sine, that'd be sine x pi?
Oh, I see. I'd have to shift it though, so it'd be like sine of x plus pi or something like that.
Yeah,
X minus pi or something. So yeah, shift it forward, shift it back. Yeah. And I did get, I can't remember if I told you guys about when I tried to write to TI to ask them how their calculator does certain things. I want to write to one of the noise canceling headphone people and say, can you give me any specifics about the formulas you use in your programming? I'd love to show it to my, I don't know, maybe I'll do that if I remember. And they'll probably say, we think you're from this other company, you're trying to steal secrets, all right? That's what TI told me. You're from HP, leave us alone. I am? Okay. Coming back to this. This is going to move it by an angle of how many degrees? 30 degrees, yes? So it's going to move it right 30 degrees. So the phase shift is right pi over 6. Now, not surprisingly then, I already know where the new function is going to start. Where's the sine start that's not been moved? 0. This sucker's been moved, so where's he going to start? Pi over 6. Okay. But if I, is there a multiplier here?
No.
So the period is still what?
Same.
2 pi still, right? 2 pi divided by 1 is still 2 pi. Is everybody with me? Okay. But we can still do step size. What's the step size going to be? Here's my period. This is how far I got to go. Divided by? No. How many steps do we take? 4. So all my steps are going to be pi over 2. Oh, did you say, you got to the answer? I'm sorry, Dylan. I wanted the middle end, not the end answer. Okay. And if I do my begin and end work, it begins when the inside is 0, so it will begin at pi over 6. Now here's where the one that's a little more interesting. It ends when the inside is what? Where does normal sine begin and end? 2 pi. How do I solve this? Gotta milk LCD. What's that?
13 pi over 6.
Good. Now, somebody semi with me. Let me pull out so you guys can see more stuff. Stay with me now. If I want to graph this, I know I start at pi over 6. My step size is pi over 2. So here's the first little thing I want you to get used to. I have to add pi over 2 to step. That's not easy. All right, let me change this into something over 6 so it goes with this. Do you see what I'm saying? You can be nice to yourself. What's this equal to over 6? 3 pi over 6. I just got to triple the top and bottom, yes? Don't look up there, Jeff. Say again? Yeah, so then first step, add 3 pi over 6. I got a 4 pi over 6. You don't have to reduce that. You could, who cares? Next step takes me to, every step I take, I go this much. 7 pi over 6. Where's the next step take me to? 10 pi over 6. Where's the next step take me to? 13 pi over 6. I took 4 steps now, right? 1, 2, 3, 4. We ended at 13 pi over 6, which is what we said we should. So again, do you guys start to see how this is really not necessary? But it's nice. I get the same answer twice, and I feel good. I've just sort of internally verified that it looks like what I got was right. So this is almost all the work you're going to have to do, because this is still a pretty easy problem. So where does sine start? So we know we start here. Where does sine start? At 0, and then it goes to highest, 0, lowest, 0. So that's what I mean, that when you're about to start graphing, that's where the easy part lives. It should be easy. We've done all the work already. The graphing should be easy. Okay. So let me do this. Do I want to? Yes, I got to do that last piece. Okay, there's one more thing we haven't talked about yet. Oh, that's why I can't see shit. Oh, thank God. That was English. Okay. I'm focusing on sine a little much, but that's okay. I'm okay with that. Yeah, let's do plus pi there, yeah. So here's the problem. Let me just tell you right now, the phase shift is not left pi. Does everybody see plus pi in there? And so normally you would say the phase shift is back pi. Well, how much would it shift? But that's not what's happening to x. How do I tell how much it moves left and right? It's dependent on how much I'm adding or subtracting from x. What am I adding pi to? 4x. That didn't tell me shit. Do I have a 4x axis? No, I have an x axis. So what do I need to do? I wish it was just x. There's a freaking 4 there. What can we do if we don't want the 4 there? We can erase it. Huh? Can't divide by 4 because it's inside of a sine. There's not an equation in there with 2 sides. I can factor a 4 out. So I'll do this part. Now real quick, what operation are you doing when you factor something out? Why is this 1x? Because what am I doing when I take a 4 out? I am dividing it out, yes? Just remember that. Whatever you put there, I'm dividing. So what's pi divided by 4? Pi over 4. So now what is happening to the x? Stay with me now. You guys are making me tired. Everybody's yawning. I'm like, come on, man. I'm barely making it myself. Now I see exactly what's going on to the x. So it's going to shift how far? I'm sorry, which direction? Left. So the phase shift is left pi over 4. Stay with me now. We're almost there. I'm going to shut up in a little bit. I don't know if anybody plays the YouTube videos just to go to sleep. If you do, it's okay. I'm glad I can do the service. What's 4? In terms of everything we just discussed, what is 4? What's going to help me find? What's 4? What's its job? What is it going to do for me? We gave it a letter earlier. True, it's going to be the accordion. So remember how I get the new period? The new period is the old period divided by that multiplier, divided by that k. Whatever's multiplying x. And don't forget, I mean, that's why it makes sense, because if I'm multiplying by 4 inside, I'm dividing by 4 because it does the opposite of what it looks like it's doing when it's inside with the x. So that's why I divide by whatever that number is. If it's a fraction, I end up multiplying by its reciprocal. Stay with me. What have I forgotten? Oh, I didn't make the amplitude in here. No, screw it. The funny thing is, if I put a 7 here, you just kind of put a 7 on your graph. It doesn't really do anything structurally, to be honest. So we'll keep that at 1. Can somebody help me figure out the step size? Yes, pi over 2 divided by 4. That's a silly way to write it. How do I divide fractions? Multiply by bubble. And then I get what? Pi over 8. So be nice to yourself. I always have people write it like this and try to do stuff here. I'm like, no. Pi over 2 divided by 4. That's what that says. Multiply by the reciprocal. For some reason, whatever word I just said, it should have been reciprocal. For some reason, students just want to be mean to themselves. I don't get it. I don't want to look at that. Now, I've done this shit enough. I know this pi over 8. Because if I cut it in half, cut it in fourths, I've cut it in eighths. But that just looks weird for a student who's not doing this a lot. So write it like that. Multiply reciprocal, bam. That word is giving me trouble today. Whatever this is, I'm going to take more. Oh, yeah. Okay. So, just to remind you guys, I'm never going to just say graph. I'm going to graph this after finding the amplitude, the phase shift, the new period, the step size. Yes, you're not going to have to remember all the parts. I'm going to tell you what they are. You do have to remember how to get them. So if I wanted to, I could do beginning and end. It always begins when the inside is 0, and it always ends when the inside is 2 pi, and it being sine and cosine. I got to be careful. Because eventually we're going to talk about tangent, cotangent, secant, cosecant. Tangent's going to be a different beast from this, so we'll talk about it when we get there. If I solve this, I get something not surprising. Why is that not surprising? What did we already figure out? We go left pi over 4, so of course I start at negative pi over 4. And then if I solve this, I get pi over 4. Now real quick, how far apart are these two? Don't overthink it. How far from this to 0? Pi over 4. And how far from 0 to this? So what's pi over 4 plus pi over 4? Pi over 2. And that is that's how long it takes us. And didn't we already figure that out? The new period. Hey, so it's a check and balance. I get the new period from taking the difference of these, and I see it is exactly what I said it should be. So maybe you're starting to see this is not necessary. You could totally do this problem without these, but it's nice. If I'm a student doing this stuff for the first time, I like this. I'm like, let me double check everything I already got and make sure it's right. So now if I want to graph this thing, wow. My step size is pi over 8, so I want to be nice to myself. I'm supposed to start at negative pi over 4, yes? How can I write this, negative pi over 4, so it jibes better with stepping by eighths of a pi? Yes. Do you guys see that? That's important. That's huge. That's just you being nice to yourself. Let me make the denominators the same at the beginning, so I don't have to do it every damn time. So now I start at negative 2 pi over 8. Where's the first step take me? Every step is this big, yes? Negative pi over 8. Where's the next step take me? 0. Keep going. All right. And then? All right. And real quick, we start at negative 2 pi over 8 and we end at 2 pi over 8. We predicted that with this work. Again, not necessary, but nice. You said that enough, Jeff. I think we get it. Okay, thank you. We're still dealing with sine. What does sine do? Where does it start? Here, we start here. So what's it? I kind of gave it away, but where does sine start? 7? Oh, 0. Okay. I thought you were just screwing that one. Starts at 1.7, Jeff. And then it goes high, then it goes 0, then it goes low, then it goes 0. It always, sine does that. I gotta be careful. The way they make this different is if I had a negative out front, because what's a negative out front do?
Go down.
Reflect it. So then it would go down, up, yes? It would just reflect around, yes? Okay. And then you just fill it in. Okay. Make whatever sounds you want to as you do it. Yes, I think we're ready. Okay, here, let me do this. Oh, wait, no. We're almost ready. Oh my God, Jeff. Let's just talk about cosine for a second. I'm sorry, did I take that away too early? Did everybody get this? I think somebody kind of gave up on it. Like, I'm not even gonna try all that crap. Does everybody get this? Okay. Please don't let me steamroll you. You can tell me. All right, is everybody good? Okay. Cosine. This will be very quick because cosine should act just like sine. All the stuff we just did is true for cosine. It's just, it doesn't start at 0, of course, because what is cosine of 0? 1. So cosine starts at the max. What's cosine of pi over 2? 0. What's cosine of pi? Negative 1, and then it goes to 0 again, and then it goes to 1 again. Okay. So cosine looks like sine, but it's been shifted. Like if I put sine here real quick. Cosine looks like if I shift sine back by 90 degrees. Do you guys see that? So if I have a cosine function, I still do all the same. I still do the steps. I still do the beginning end, I still do the new period, but now when I go where I start, it starts at 1. Not at 0, it starts at 1. And then I go through my steps. You guys said all with me. If I have a sine function, it starts at 0, and then it goes up, blah, blah, blah. If I have a cosine function, it starts at 1, and then it goes down to 0, down to the min. I still do all the same work, the step size, the new period, all that kind of shit. It's all the exact same work. It's just what does it do at those steps? It's different. So, finally, dear God, Jeff. Every time it's worse. Okay, here. I have a workout example on the front. And then I have a problem for you to try on the back. Are those noise canceling?
Yeah.
Neat. How you doing? So if you look on the back, I want you guys to try that out. Try to do as much as you can, and then we'll do this together. And you can work with whoever you want to work with. I'm not going to force you into a group today. If you're like, I never like working with anybody, Jeff, well then today's your day. You can work all by yourself. Just be really honest. So remember, one of the first things you want to do is that factoring step inside. So just make sure everybody's on the right track. What am I going to want to factor out inside of the cosine? 1/2. And just be careful. Look at 1/2. So what are you going to take out of the top? 1. What are you going to take out of the bottom? 2. If you look at it like that, the pi over 8 is pretty easy to tell what it becomes. Try it out. You can show me before you keep going if you want to make sure it's right. Let me catch up to you. K is always that multiplier, or it's the thing you had to take out. They both, in this case, are 1/2. So K is 1/2. Amplitude's the easiest question I could ask you. 2. Period is always the original period divided by K. 2 pi divided by 1/2 is 2 pi times 2, which is 4 pi. So this is going to end up stretching it. Okay. So it's like holding a spring, one of those old like gym things where you would stretch it. Phase shift. Since we factored this out, we know exactly what's happening to x. We just have to remember our transformations we went over before. This is going to move it by how much? Pi over 4 to the right. And my step size, I always take 4 steps. In fact, this is cool. Every trig function we're going to look at, they're going to take 4 steps. So this is going to stay the same forever. It's going to be the new period, which was 4 pi. That's how far are we going to go, divided by how many steps I'm going to take. So every step is pi big. I like that. Every step you get a pi. It sounds good to me. And again, the more we do this, the more you're going to start to realize this is really nothing you have to do. In fact, on a test or a quiz, I say you can do that if you want to. You don't have to do this. But if I do this, if I add pi over 8, what do I do to both sides to get rid of the 1/2? Multiply by 2. These reduce. I get pi over 4. Why is that not surprising? Because how much do we shift by? Pi over 4 to the right. So it makes sense. I normally start at 0. Now I'm going to start at pi over 4. And if I want to do the end cycle. Now here's something you could do. Watch this. You guys ever done this before? Do you see all these fractions in this damn thing? What would the LCD be? What would the LCD be? What would the LCD be? Don't overthink it. What's happening out there? No. 8. What denominator would make everybody the same? 8. So if I just multiply by 8, this side is 16 pi. What's 1/2 of 8? 4. And what's 8 times pi over 8? The 8's cancel. So look at that equation. Doesn't that look much better? So if you have an equation, you're allowed to multiply both sides. If you multiply by the LCD, you will kill all of your fractions. They are all dead. Yay. Again, not a life lesson, kids. So then I add pi. Now it's a relatively easy little. So then I divide by 4. Now, real quick, does anyone see why it's good we got this? How far does this go? Starts at pi over 4. It goes to 17 pi over 4. How far does it go? 16 pi over 4, which reduces to 4 pi. That is the period, because that's how long it takes the cycle to complete, and we already knew. I'll calm down. The period is 4 pi. Okay. So again, this feels like a lot, I know. But if you just break it down to each piece of this is not that bad. And then this is unnecessary, but it's nice because you kind of verify what you saw. Has anyone gotten to the point where you graph this thing yet? Okay, everybody try to graph it. Now that I've double checked everything. If you got all this, you got it all right. Now try to graph it, and then I'll catch up to you. And then, for a little extra motivation, when you're done with that, we're gonna leave. I have nothing. Just need time. The last couple days have been weird. So you guys get to enjoy me giving myself a break. Yay. Okay. And see the step size, by the way? Do you see how we reduced it? But do you see how I actually want to use that? They're the same thing. I can use either one. So try to graph that. You know how big each step is. I would use 4 pi over 4 so that it goes well with where I have to start. Just set up the steps. And you gotta remember doing cosine. You gotta remember the amplitude. Well, it's not actually that. It's got to be curved, Jess. This is going to curve forever. Which your step size is 4 pi. So if you start at pi over 4, the next step should be 5 pi over 4. Yeah. I think you're trying to do a base graph and shift. You don't have to do that, thank God. That would be so horrible to do here. Remember how we used to do it? You do a base graph and then you shift? That would suck. That would suck big time to do that with trig functions. What's my first step in?
5.
Yes, because every step is 4 pi over 4. I don't want to use this. I want to use that because that goes along with this guy. So every step I take is 4 pi over 4. So what's the next step? And then I add 4 pi over 4. And then I add 4 pi over 4. What's nice about that? We predicted it. Look. We're Nostradamus. Okay. And my amplitude is 2, so let me go ahead and remind future me. Hey, future me, don't forget, you gotta go freaking 2. And we're graphing what function? Cosine. And where does cosine at the first point here, where does he start? That's right. He starts at the max. And then he goes to 0, and then he goes to the min, and then he goes to now, I would have said this no matter what, so I'm not picking on anybody, but you don't connect these with straight lines. This is not an absolute value, yes? I know it looks like it when you graph these points, but we just picked points off of a graph. I can make any graph look like anything if I just pick certain points from it. But we know when we put the meat on these bones, you've got to curve your way through these so that it can continue forever. And if I did go a little bit further, you would see a sine piece, something that looks like sine, because sine and cosine are just each other, just shifted a little bit. Yes. So as I just said, we're going to stop there. And I'm going to get some frickin' time to just be. This is going to be so good. Do that for yourselves when you can. It's good to be the teacher. Do that now. All right. I'll see y'all tomorrow.
Have a good day.
You too. Trent's all over that. Trent's like, I'm out of here.